All right, so we've covered the first part of the fundamental theorem of calculus and did a couple of examples with it. As important as it is, we're not going to be using the first part of the fundamental theorem directly a whole lot outside of this section. It will show up, but its primary purpose for us is to prove the second part of the fundamental theorem of calculus, which you're going to be using all the time. So let's get into that second part. Okay, here it is. Fundamental theorem of calculus, part 2. If f is continuous on the closed interval ab, same assumption we made in the first part, then the definite integral from a to b, notice there's no x's here, it's the endpoints of this interval. The definite integral from a to b of f of x dx is equal to capital F of b, my upper limit of integration, minus capital F of a, my lower limit of integration, where capital F is any antiderivative of little f. That is, any function capital F for which f prime, big F prime equals little f. This is why we spent the end of chapter 4 talking about antiderivatives. It was entirely because this is where it was leading us. We use antiderivatives to evaluate integrals, definite integrals specifically. So let's prove this really quick, and then let's do some examples with it. Let g of x equal the integral from a to x of f of t dt, the same integral defined function that we keep coming back to. Okay, we know from the previous part that we just talked about that g prime of x is equal to f of x. Differentiating this integral defined function, leaves me with the integrand f of x. The t is replaced by an x. Okay, but this is another way of saying that g is an antiderivative of f. After all, if f is the derivative of g, then g is the antiderivative of f. That's how that works. Okay, but let's suppose that capital F is any other antiderivative of f, little f, on the open closed interval a b. We talked about the form that an antiderivative will take all the way back in section 4.2, even though we didn't use that terminology then. We showed that if capital F and g are any two antiderivatives of little f, that they have to differ by a constant. And another way of writing that is capital F of x is going to be equal to g of x plus some arbitrary constant, which we call a constant of integration. Okay? And this will be true for any x in between a and b. So we know that both capital F and g are continuous on AB, and that's from the first part of the fundamental theorem of calculus. These actually, no, it's not even from that. It's the fact that if these are both antiderivatives of little f, then we have to be able to take their derivative to get f. But if we can take their derivative in the first place, they must be differentiable. And from chapter 3, I think, or the end of chapter 2, we know that if a function is differentiable, it must be continuous as well. So these two functions are continuous. And that means if we take the limits of this equation here, as x goes to a from the right or to b from the left, because we have to approach a and b from inside this interval here, the equation we'll see also holds when x equals a and x equals b. So all of that is just to say that capital F of x is equal to little g of x plus c for every value in my closed interval AB. Okay. Now, if we plug a into the formula for g of x. So again, we define g of x right here at the beginning of this proof. If I plug a into this, then a goes into my upper limit of integration, and I get the integral from a to a of f of t dt, which is going to equal 0, because my upper limit and my lower limit are equal to each other. If I plug a b in for this, which we're going to do down here, let's see what happens. So capital F of b minus capital F of a, which is the thing that's showing up in the statement of our theorem here, would be equal to, using this equation, g of b plus c minus g of a plus c, but the minus here is going to cancel these two constants of integration out. The c minus c is going to go to 0, leaving me with g of b minus g of a. We showed up here that g of a was equal to 0, so this is really just equal to g of b, but g of b by definition is what we get from plugging b into the upper limit of integration in this guy right here. So we end up with the integral from a to b of f of t dt, which is exactly what we were trying to show, that that integral was equal to capital F of b minus capital F of a right there, okay? That's the whole proof. Sorry, you can probably hear my dog drinking water in the background. It's very loud. We're going to evaluate some definite integrals now using this theorem, and we're going to show how much better it is to use this theorem than to try to use the limit definition of the integral, which was fairly involved when we had to do that. Let's start with this guy. We want to evaluate the integral from 0 to 1 of x squared dx. Now I'm doing this one specifically because we spent a lot of time talking about this definite integral back in, I think, section 5.1, before we were even calling it an integral. We were trying to find the area under the curve y equals x squared from 0 to 1. And we eventually got there. We found out that it was 1/3. But that was after using our limit definition. What I want to do now is use the fundamental theorem of calculus to show that I get the same result, but in a much easier way. So how do we evaluate this? The integral from 0 to 1 of x squared dx. Well, the key is to find an antiderivative for this integrand, x squared. Remember, it says here, if little f is the integrand, then big F is an antiderivative of that, and the difference between big F of b and big F of a is how I evaluate my integral there. So this thing has several antiderivatives, but I'm going to choose the simplest one, x cubed over 3. Any other antiderivative would look like x cubed over 3 plus some constant. But we showed here that the constant, if I did include it, is going to cancel out anyway, so we may as well just leave it off. Now that I have this antiderivative, I'm going to introduce a new notation here. I'm going to put a big vertical line there, and I'm going to write 0 and 1, my lower and upper limit of integration. And what this notation means is that I plug my upper limit in first, so I get 1 cubed over 3, and then I subtract the lower limit plugged in to that, 0 cubed over 3, because that's what the fundamental theorem of calculus tells me to do. I take my antiderivative, plug in my upper limit, subtract my antiderivative evaluated at my lower limit. This, of course, is just equal to 1/3. And that was easy, right? That really wasn't that bad. Okay, let's try another one. Now I'd like to evaluate the definite integral from 1 to 4 of 1 over x dx. Okay, the integral from 1 to 4 of 1 over x dx, which, by the way, I'm going to write this. You will see this a lot more in calculus too. Oftentimes we treat this dx as if it were a number that's being multiplied somehow, and we can write this as well, dx over x. These are the same thing. Okay, it's kind of like I multiply the dx into the numerator there. You'll see either one of these written. But what is this equal to? Well, I need to find an antiderivative of 1 over x, and we have one. We know that the natural log of the absolute value of x is equal to, or is an antiderivative for this, because the derivative of that is 1 over x. I'm going to evaluate that from 1 to 4, which means the natural log of the absolute value of 4, which is really just that, minus the natural log of the absolute value of 1, which is just that. Okay? I don't know why I included the absolute values there. I'll include it there just for completeness. The natural log of 1 is equal to 0, and so all I'm going to be left with is natural log of 4. I'm not even going to put that in a calculator. I'd prefer to leave it in that form. Okay? That's not bad. We can knock these definite integrals out much faster now that we have this technique. Okay, now I'm going to evaluate one involving a trigonometric function. I forgot to type dx in here, so I wrote it. That's why it looks a little sloppier. This is the integral from pi over 4 to pi over 3 of secant squared of x dx. Okay, so this one, secant squared of x, can you think of an antiderivative for that? Let's see. Pi over 4, pi over 3, secant squared of x dx. Secant squared should ring a bell. That's the derivative of the tangent function. So its antiderivative would be the tangent function. Tangent of x from pi over 4 to pi over 3, which is the same thing as tangent of pi over 3 minus tangent of pi over 4. Okay, tangent of pi over 3 is root 3. Tangent of pi over 4 is 1. And I'm going to leave my answer in this form. I could plug it into a calculator, but this is exact, whereas a calculator is going to give me a number I have to round. Okay. Next one. Let's evaluate the integral from 1 to 2 of this function here, 3x cubed minus x all over the square root of x. I can tell you right now, a big proportion of you learning this for the first time are going to be tempted to try and take the definite integral of the numerator and put that over the definite integral of the denominator. And that doesn't work. We addressed this in section 4.9. That would not give you an antiderivative of that function. If that were the case, then we wouldn't have a quotient rule. The quotient rule would just be taking the derivative of a numerator and the derivative of a denominator and keeping them there. We know that it doesn't work that way. So what we saw in 4.9 was that it's better to simplify this into something that's more manageable. This is the same thing. If I were to convert these into, this radical into exponents and then use some exponent properties, this would be equal to 3x to the 5/2 power minus x to the 1/2 power, right? Hopefully you can see where I would have gotten that from. And this, I can find antiderivatives of this fairly easily. I want to point one thing out. Notice that I put parentheses around my integrand in this case. That's necessary anytime you have more than one term in your integrand. I didn't do it here because I only had the one term there, but you need to put parentheses when you have multiple terms in your integrand. Otherwise, notationally, it might mean something different. So how do we evaluate this? Well, I need antiderivatives. So remember how it works for the power rule. We start by adding 1 to the exponent, which would be 7/2, and then I multiply by the reciprocal of that. Same thing as dividing by that. So 2/7 times 3 times x to the 7/2. Okay, minus what would this be? So I add 1 to my exponent, which would give me 3/2, then I multiply by the reciprocal of that, 2/3 x to the 3/2. Now I'm going to put these in square brackets, and I'm going to write this. So this right square bracket is filling the role of this vertical line here, and that notation is very, very common as well. You typically see that in a case like this where you have multiple terms that all need to be grouped up. So let me simplify just a little bit. This is equal to 6/7 x to the 7/2 power minus 2/3. Whoops, I wrote 3/3. It should say 3/2 there. X to the 3/2 power. Okay, and again from 1 to 2. So what is this equal to? Well, I start by plugging in my upper limit of integration. This is 6/7 times 2 to the 7/2 power minus 2/3 times 2 to the 3/2 power minus, now I plug in my lower limit of integration, and you have to be careful here. Put parentheses around this because there's more than one term, right? So I have 6/7 times 1, we'll use little dots here, 1 to the 7/2 power minus 2/3 times 1 to the 3/2 power. And for me, I think I'm going to, should I leave them in rational exponents or should I get some radicals? I think I'll get some radicals out of this. So this is equal to, let's see, 2 to the 7/2 power. Well, 2 to the 6/2 power is 2 cubed, which gives me 8. I can multiply that to the 6 up here to get 48, and then I have this root 2 left over 7, minus, this would be the same thing as 2 root 2, multiplied to that 2 gives me 4 root 2 over 3, and then the ones here are all 1, so I get minus 6/7, minus is going to give me plus 2/3. I guess I could combine these two guys since they have common denominators, and these two guys, I don't really care so much to do that. I'm just going to leave this in that form. I'm happy with that. Okay? We're getting close to the end here. So I want to do an example where the fundamental theorem of calculus, if you apply it without thinking about it, gives you something that seems contradictory. So this one right here, explain what's wrong with this computation. I want to evaluate the integral from -1 to 3 of 1 over x squared. That's the same thing as x to the -2nd power, right? Its antiderivative, one of its antiderivatives is -1 over x. That's an easy one to verify. So there's nothing wrong from going from here to here, technically, as far as the antiderivative part is concerned. Okay? There actually is something wrong going from here to here, but that's not what it is. It's not the wrong antiderivative. I have -1 over x. Then if I plug a 3 into this, I'm going to get -1/3. If I plug -1 into this, I get -1. So that gives me a +1, but I'm supposed to subtract that. That's what I do with that lower limit of integration. So I get -1/3 minus 1 equals -4/3. The reason there's a problem here is because the function 1 over x squared is always positive. Think about it. I'm squaring something. I should only get positive numbers there. And we showed back in the previous section where we talked about properties of the integral, if you take the definite integral of a function that is positive everywhere on that interval, then the result has to come out positive. And yet we're coming out with a negative number. Why is that? Well, the reason why is because the fundamental theorem never applied to this integral. Why? Because the fundamental theorem of calculus right at the beginning says if f is continuous on that closed interval. This function, 1 over x squared, is not continuous on the interval from -1 to 3. It has a discontinuity at 0. So that is the reason this is coming out wrong, because the fundamental theorem of calculus never applied in the first place. Now, if I took the definite integral from 1 to 3, I would have gotten a correct answer because this function is continuous on that interval, but it's not going to be continuous on any interval containing 0. And so I'm going to get weird results if I try to apply the fundamental theorem there. Okay, that's the problem. I'm not writing it out. I'm just going to talk that one out. All right. One last kind of fun example, I think, is this one. We're going to define g of x as an integral defined function again. It's going to be the integral from 0 to x of f of t dt, where the graph of f, the integrand, is shown down here. We want to evaluate 3 things: g of 3, g prime of 3, and g double prime of 3. So let's start with g of 3. What is g of 3 equal to? By definition, it's the integral from 0 to 3 of f of t dt, which means it's the area under the curve from 0 to 3. And let's look at that. It's this guy right here, okay? How can we cut this thing up into parts so that I can easily easily find its area? Well, let's see. I'm going to shade this in just to indicate what we're looking for. I think what I'm going to do is actually take a look at this triangle here first. So you notice I have this triangle, which has a base of, actually, no, let's do, what should I do? We've got a, Let's start with this triangle right here. You have to think about how to cut this up into manageable chunks. This triangle right here has a base of 2 and a height of, what's this? 1, 2, 3, 4, 5. Okay, so the area of this triangle is going to be 1/2 times 2 times 5. 1/2 times 2 times 5. Okay. Now what's left? We have to get this area right here. So I see a rectangular region right here, and it's a 1/3. I'm just counting the squares there, basically. So that's an area of 3. And then I have another right triangle right here that has a base of 1 and a height of 2. So that's plus 1/2 times 1 times 2, using my area formula for a triangle again. So what does this come out to? That's 5 plus 3 plus 1. That's 9. Okay, so g of 3 would equal 9 because that's what the area under that curve is. It's 9 from 0 to 3. What about g prime of 3? Here's where we're going to use the fundamental theorem. G prime of 3 is the same thing as f of 3. That's what the fundamental theorem says. G prime of x is equal to f of x. So this is just finding where f of 3 is, and it's the y coordinate of that point, right? Because this is the graph of f right here. 1, 2, 3. It's equal to 3. Not bad. What about g double prime of 3? Well, if g prime is equal to f, then taking the derivative of g prime is the same thing as just taking the derivative of f. G double prime is the same as f prime, which means now we're looking at the slope of the tangent line to the function f at the point 3, or at where x is equal to 3. But that portion of the graph is a straight line anyways, so I can find the slope just by looking at it. Going from, say, this point to this point on that line segment, we're going down 2 units and over 1. So we have a rise of -2 and a run of 1. That's -2 over 1, or just -2. Okay, so the slope there is -2. I like examples like this, or exercises like this, because it really gets you thinking about the integral, the derivative, and the connection between those things. That's going to wrap up section 5.3.